activation functions. When you hear this term activation functions, the first thing that should come to your mind is non-linearity. Why is it so? The reason is activation functions are mathematical functions that are used in, specifically here we are talking about neural networks. What happens in a neural network? In neural networks, activation functions are used in order to introduce non-linearity into the neural network. This is the main point. What did I mean by non-linearity? Basically, it decides whether on a particular neuron, when you give some particular input here, whether you should fire this neuron or not. Or maybe it decides how much should it fire. That is, whether this neuron should be activated or not, or how strongly should it be activated. So this is where the term activation comes from. Okay. Next thing is, what did I mean when I say activating a neuron? What is this purpose? First, let us understand this from a neural network point of view. Let us say this is your input, and then you have another layer, and so on. Let us say you have some layers of this neural network, neurons, and then you will reach final layer. How will the input come up? Some input that would reach this particular neuron, the input layer. Then it will come to the next layer, to the next layer, and so on. Let us say it can go in any way to different neurons. Finally, it will reach the output layer. So when it reaches the output layer, you are expected to get the output. The question here is, what exactly happens at each neuron? At each neuron, when something reaches let us say some input reaches, let us take this neuron for example. When some input reaches here, either this neuron should be activated or it should not be activated. That is, either it should let some information to pass in some particular manner, or it can block that information, or it can decide how it should pass or how strongly it should pass. This decision is in the hands of your activation function. So what I mean here is, once you get an input, you will generally multiply it by weights. You will have different weights in that neuron. When an input is coming in, that input will be multiplied by weights. Then you may do addition of bias. These are the two things that you generally do. What did I mean by these things? Let us say you have some input x1, x2, x3, so on up to xn. What happens at one particular neuron? It will create y is equal to w1 x1 plus w2 x2 plus up to wn xn. So what are w1, w2, w3 here? These things are the weights that are present in that neuron. Let us say there is some bias term as well. So this plus bias. Like this, the neuron is going to do calculation at that particular neuron. But if you simply do this calculation, which is multiplication and addition, it can only do a linear transform on the input. That is, you are multiplying it by some particular value and then you are adding it. That means it is a linear transformation that is happening to this particular input. But what is the purpose of this complete neural network? Why are you constructing a large neural network here? The whole purpose is you want to model a complex one. That is, whenever you have a complex model, you have a complex task at hand, which you can't generally directly model using traditional programming. That is when you are actually coming to these neural networks. Otherwise, if you directly know how you can do the program, you will directly write a code and complete the program. You don't need a neural network at all. When do you want this neural network? When the task is so complex that you cannot actually write a program for this because the logic is very complex or cannot be programmed. And in that case, you take help of neural networks. This means you want your neural network to be able to model complex functions. And that is where, when you want to model complex functions, that is where activation function comes up. So this is without activation function. Then what you do is, you will apply the activation, and activation will look something like this. A is equal to, you can say, f of y, and this f is your activation function. What this does is, this particular transform will be non-linear. Because it is non-linear, at each neuron you are giving the neurons the ability to do a linear transform and then an activation, which is a non-linear transform. So each of these neurons are now capable of doing non-linear transformations. So even if you have a very complex function to be modeled, still all these non-linear transforms can together give you any sort of complex function that you want to model. This is the logic using which neural network is going to work. So this is the use of activation function. How you want to understand this is, let us say there is no activation function in this network. Then what will happen is, even if you stack in a lot of layers, here I am having these layers, let us say you have even more layers, a lot of layers here, still each of that layer will just be a linear transform. Now think about this. If you are having each layer as linear transform, then you added a lot of layers. What will happen? Even though you added a lot of layers, it is still only a linear transform. So there is kind of no point in adding all these layers, because it is still only a linear transform. If you want to model complex functions, then you want non-linear transformation, for which simply adding layers won't help. Instead, at each layer you should do activation, and this activation will help you in your non-linear transformation. So this is the logic. Okay, so this part is what you want to understand. That is, at each neuron, when input is received, what you do, you multiply them by weights, and then you will sum them up and add the bias. This is what we generally call as a linear calculation. But this activation function, this thing that I additionally added, this introduced non-linearity. That is, the entire network can now function in non-linear manner. It is not a big linear transform. This is the difference. Okay. So at this point, you know, in order to solve complex problems, you need non-linear transformation. What I'll do is, I'll give you an example so that you can understand what is this non-linear transformation. Okay, that will be better. Just think about this. Let us say you want to invest some money. Okay, you are investing some money. When you are investing, what you did is, instead of, you can simply write a program for calculating how much money would increase each year. But because I'm teaching you neural networks, because I want to put in as an application of neural network, just imagine, okay, for understanding purpose, just imagine that you built a neural network in order to give you an output. That is, if you put this much of money, then at the end of this many years, after a particular time period, how much money will you have? That is, in the bank, if you invested some particular money, a principal amount, then you waited for these many years. After that point, what money will you have? This is a bank which is offering, let us say, simple interest. You are considering simple interest. What happens in simple interest? What happens is, let us say 100 is your initial amount. Then if the bank is providing 5% simple interest, at the end of first year, you will have 105 rupees, because 5% is added on to this. At the end of second year, what happens? This will be 110 rupees, because again 5% of the principal amount got added, 5 rupees. At the end of third year, what happens? It will be 115 rupees. This is a linear transformation which you can easily model without using any activation function. So this is how simple interest calculation worked. But what if instead of simple interest, generally all banks will provide compound interest. So instead of simple interest, if it is a real world scenario where you are having compound interest, there is compound interest, and you want to calculate what will be the amount at the end of third year. This time it is not as simple as this, because in the first year it's okay. In the first year, what happens? You got 5%. Let us say interest rate is still 5%. In the first year, you got 5% of 100 as interest. But what happens in the second year in case of compound interest? Because it is compound interest, it is not going to be directly 110. Instead what happens? 5% of this 105 will be calculated. So 5% of this plus whatever you already had. This will be what you have in the second year. What happens in the third year? Whatever is this total amount, 5% of that plus this amount that you had. So this is a non-linear transformation now. Getting the point? So previously we had simple interest, which was linear transform. It was easy to model, but this time it is compound interest. Without an activation function, there is no way you can implement this in a neural network. See, if you again ask me, why do you want neural network for this? You really don't need neural network for calculating simple interest and compound interest. I'm just giving a case so that you understand why activation function is required. Okay. If you imagine that you are modeling these two using a neural network, then simple interest case is a linear transformation which you can easily model without an activation function. But if you want compound interest, then it is not a linear model. It is a non-linear transform for which activation function is necessary. So this is where I want you to understand what exactly is an activation function and how it works. Next thing that you want to understand is, when I said it will apply non-linear transformation, what should be the specialities of this particular function? This activation function, it should have some specialities because of which it is qualified as an activation function. What are those specialities? So first thing you already discussed, it is non-linearity. It should be able to introduce non-linearity into the model so that complex functions can be learned. This is the first point. Second point is, we already learned that whenever you have a model or a neural network and you pass an input through this and you got some output y cap, the most important part is to calculate loss by comparing it with the actual input y and then back propagating this loss. While back propagating this loss, let us say using gradient descent or something, then we already discussed in all our previous lectures that most important part is you should be able to differentiate it and then back propagate. So because of this, differentiability becomes an important factor for activation functions. Only if you can differentiate it, then only it will be easy for you to back propagate your loss whenever you are getting calculated the loss. Because of this, differentiability is an important factor. One is non-linearity. It should be able to introduce non-linearity to the model. It should be a non-linear function. Second thing is differentiability. That is, the activation function must be differentiable. So there are cases where we'll discuss it. When we reach those activation functions, we'll see when it cannot, if it is not differentiable, how do you handle those things, we'll see. Generally, you can say it should be differentiable. Okay. And one more thing is monotonicity. Why do you want monotonicity? This again is related to optimization. So it will be clear when we reach optimization lectures. For now, just understand that when I say monotonicity, that means derivative won't change sign. Okay, derivative won't change sign, and because of this, your optimization becomes easier. When we reach optimization lectures, there we'll see in detail what exactly these things are. Okay. And okay, finally, you know what is the purpose of all these things? It should be able to mimic that logic of human neuron. That is, when something reaches this neuron, some signal reaches this neuron, it will decide whether the signal should go forward or it should not go forward, or how it should be transformed and put forward. So this is what you are trying to mimic with an activation function. What are the different activation functions? This is also important. You should know what exactly is an activation function. So in the coming lectures, we'll see that there is something called as sigmoid activation function. There is something called as tan H activation function. There is something called ReLU activation function. There is something called leaky ReLU activation function. Many of these activation functions are there. Then there is softmax. We'll learn in detail about each of these activation functions and what exactly is the use case of this function. See, whenever you are learning something, there are two important things. One is you should understand what it is. That is very basic. Secondly, you should understand where it is originating from. What is the logic behind using this thing? What exactly is the logic? You should understand it logically and you should understand it mathematically. Then only you will get the clarity on that concept. And finally, you should know where to use this. If these things are clear, then you can say you understood this topic. Okay. So this is it about activation functions. In the coming lectures, what we'll do is we'll go through each of the activation function in detail. Then we'll understand under what situation, under what cases should you use which activation function and what is the logic behind it. Okay.